Alright, so this is Griffiths Quantum Mechanics, problem 1.7, where basically we are going to be calculating the time derivative of the expectation value of momentum, and Griffiths actually gives us the answer to this, so we know kind of what we're shooting for. So it's the expectation value of minus the x derivative of the potential, like this, right? So basically this side here is it's a term from a conservative force, so a force that's functionally a position, and the negative gradient of a conservative potential is the force. I'm not sure if all of that came out right, but so for a conservative force, it can be written as the negative of the gradient of the potential. Hopefully I didn't slaughter it too bad the first time, but all right. So this is an example of Ehrenfest theorem, which just basically says that the expectation values in quantum mechanics will follow the classical equations. So this is basically straight from Newton. The time derivative of potential or of momentum is equal to the force. All right, or the sum of forces, but in this case, just this force. All right, so I'm going to start with an expression for the expectation value of momentum that Griffiths gives us in equation 1.33. So this is just a convenient place to start this. Make sure I write this down right. Okay, all right. So here's where we're going to start, and then we'll just take the time derivative of this. And we'll move the time derivative inside. And using the product rule, we'll get these partial derivatives. Okay, now we're going to use integration by parts, which just basically, in this case, since we're integrating over x, it means we can, any one of these x derivatives, we can switch it to the other variable. So from psi here to the conjugate of psi, we can move this over here. And because wave functions all go to 0 at infinity, we don't have to worry about a boundary term, and we just get a minus sign here. So go ahead and do that. You can do it on this one too, and start with the second derivatives on each of these terms, but it might turn out a little bit longer. All right, so we get a minus sign, and then we're moving the x derivative over to this one. Can't move the t derivative, only the x one, because that's the what we're integrating with respect to here. Okay. All right. Now we're going to plug in the Schrodinger equation. for these time derivatives. So write this first part out. So we remember what we're doing here. All right, now Griffiths gives us these nice little forms for the Schrodinger equation. He just divides by I times h bar. These are equations 1.23 and 1.24. So that's what we're going to be plugging in here. All right, so I'll probably write one term here and one term below it just to due to space. Okay, so this right here and this right here, that's where we're plugging this in. Okay, so see what we got. Minus h bar 2m, second derivative of the conjugate wave function plus I over h bar times v times the conjugate wave function. All right, and then we still have this derivative here. That. All right, now we'll move to the next one. We have a minus sign, and then we have our x derivative. That. Now we'll plug in the Schrodinger equation. So this is equation 1.23. All right, so that's and this is just the Schrodinger equation once you divide both sides by I h bar. Okay. All right. That looks right so far. So let's see what we can do with this. So now if I take, I'm going to look at this term here and this term here. So these ones, we're going to cross our fingers and hope that they cancel out. If I bring a minus I h bar over 2m out front, okay, so now we have the second derivative of the conjugate wave function with respect to x times the first derivative. Like that. Okay, this minus sign came out here, so now it's a plus. And now we have one spatial derivative with respect to x and two spatial derivatives with respect to x on the normal wave function. Okay. All right, so that's those two terms. And now let's see. We're going to bring out this I over h bar. Okay, now we have a v and then the conjugate wave function, and then we have that. Okay, and then this minus sign and this minus sign will give us a plus. Okay, I think we're good there. All right. Okay. Now let's see what we've got here. So, so we notice here with these two terms, basically we just need to move one derivative from, if just say we pick this term, we want to make it look like the other one, we need to take one of these x derivatives and move it over to the conjugate wave function right here. So it's just integration by parts again. You can swap the derivative over and you pick up a minus sign. The boundary term goes away because wave functions are 0 at plus minus infinity. So once we do that, we'll end up with two x derivatives on the conjugate wave function and only one on the wave function itself in both of these, except we'll have a minus sign right here. So that's why this whole term here will go to 0. Integration by parts, we get a minus sign. All right, so that's great. And furthermore, we see that this h bar and this h bar will cancel, and I times minus I gives us 1. So this is simplifying really nicely. Go ahead and write it out again. Okay, so the I h bar parts go away, and now we have v times psi star okay, so these things all nice here. All right, so here's what we're down to. All right, so what we're going to do now, we see we have the derivative on this one, but not on this one. Basically, for the third time, we're going to use integration by parts. But that's a little teeny bit more complicated because it's not just two variables in here. There's psi star and v. So what we're going to do is move, let's just say, we'll just focus on the first one here. Why not? All right, so we'll get a minus sign, and this derivative will be with respect to v times psi star, and then we just have, try to put this in brackets to make sure it's kept separate from this one. Took the derivative off of this one, moved it on to the other two as a group, and we picked up this minus sign. All right. Okay, so now we need to use the product rule again on this. So we just have this, and then minus sign again. Oops, what did I do? Yeah. I drew that badly. Alright, but anyway, basically derivative here. Alright, and then they're both multiplied by the normal wave function. I'll just keep that outside for now. Alright, and then we have a plus extra with respect to psi star, v, normal psi, and then dx. All right, so what we see, where are we? This one. So we have this psi star derivative, we have a v, and we have a normal wave function. So this term with the minus sign is the same as this term, and they subtract out. So that's nice. We're down to our final destination here, which is we have this psi. I'm just going to write it in this form. Put this in nice parentheses here. I'm going to just draw a line down here to keep this separate. All right, so what we see here is what we came looking for, which is expectation value of the negative x derivative with respect to derivative with respect to x of the potential right there. So the time derivative of the expectation value of momentum is equal to the negative x derivative of the potential, the expectation value of that, which, if we look way back, this is what we wanted to prove. So we have the expectation values in this example, according to Ehrenfest theorem, or in support of Ehrenfest theorem, that says that the expectation values will follow the classical